The region D above lies between the graphs of y equals 2 minus the quantity x plus 3 squared and y equals negative 2 plus 1/9 times the quantity x plus 5 cubed. We're going to be describing the region in two ways, first using a top and bottom boundary, then a right and left boundary. Before we do this though, let's match up these functions to the graphs. We should be able to recognize this first function, y equals 2 minus the quantity x plus 3 squared, would be a quadratic function. And if we expanded this, the coefficient of the x squared term would be negative, and therefore the graph is a parabola opening down. Which means this piece of the graph would have to come from the function y equals 2 minus the quantity x plus 3 squared. Which means the bottom graph would have to come from the function given here, y equals negative 2 plus 1/9 times the quantity x plus 5 raised to the third. Let's also identify some of the points. Notice this point here would have coordinates negative 5, comma, negative 2. This point here would have coordinates negative 2, comma, 1. And notice the vertex of the parabola here would have coordinates negative 3, comma, 2. Now let's take a look at number 1. If we visualize the region having top and bottom boundaries, express the boundaries as functions of x and provide the interval of x values that cover the entire region. So notice how the top boundary would be the graph of the parabola here, and we already know it's y equals 2 minus the quantity x plus 3 squared, which is already expressed as a function of x, which means g sub 2 of x, the top boundary, would be equal to 2 minus the quantity x plus 3 squared. And the bottom boundary is this graph here, which we already know is y equals negative 2 plus 1/9 times the quantity x plus 5 cubed, which is already a function of x, which means g sub 1 of x would be negative 2 plus 1/9 times the quantity x plus 5 raised to the third. Now we're asked to determine the interval of x values that covers this region, and that's why it's important to have these key points here. Notice how the leftmost point of the region has an x value of negative 5, the rightmost point has an x value of negative 2, which means the x values that cover this region would be the closed interval from negative 5 to negative 2. For number 2, if we visualize the region having right and left boundaries, then the right boundary must be defined piecewise. Express each as a function of y for the provided intervals of y values that cover the entire region. So notice how for the right boundaries we have the closed interval from 1 to 2 for y, and then from negative 2 to positive 1. Let's take a look at why this is on the next screen. If we analyze this graph closely, notice how the right boundary, starting at the top, would be from here to here along the quadratic function, and then from here to here along the cubic function. So here's the closed interval for y from positive 1 to positive 2, and here's the closed interval for y from negative 2 to positive 1. And we need to express these as functions of y, which means we need to solve both of these equations for x. So let's begin by doing this. If we have y equals 2 minus the quantity x plus 3 squared, to solve this for x, let's go ahead and add this quantity to both sides and also subtract y from both sides. So we'd have the quantity x plus 3 squared would be equal to 2 minus y. And now we're going to take the square root of both sides of the equation. But when we do this, remember we're going to have plus or minus the quantity 2 minus y on the right. So now we have the quantity x plus 3 equals plus or minus the square root of 2 minus y. And now we'll go ahead and subtract 3 on both sides. So we have x equals plus or minus the square root of the quantity 2 minus y minus 3. So notice how we could have x sub 1 equals positive square root the quantity 2 minus y minus 3. We could also have x sub 2 equals negative the square root of the quantity 2 minus y minus 3. So we need to decide which of these two functions of y give us the left side or right side of the parabola, because we only want the right side. To do this, we'll evaluate both equations at, let's say, y equals 1. So if y is equal to 1 using this equation, we would have the square root of 2 minus 1, or the square root of 1 is 1, minus 3, which is negative 2 for x. But if we substitute 1 for y here, we're going to have the opposite of the square root of 1, which is negative 1, minus 3, which is negative 4. Which means the equation x sub 1 would give us this point here on the right side of the parabola. And notice that negative 4 comma 1 is this point here on the left side of the parabola. When we're defining the right boundary, we want the right side of this parabola, so we're going to be using this equation here when y is on the closed interval from 1 to 2. And again, if x is equal to the square root of the quantity 2 minus y minus 3, because x is equal to f of y, we can say f sub 2 of y is equal to the square root of 2 minus y minus 3. So going back to the previous slide, again, this is going to be the square root of 2 minus y minus 3. And now for the right boundary when y is on the closed interval from negative 2 to 1. Again, this is on the cubic function here. We need to solve this cubic function for x to have a function of y. So now starting with y equals negative 2 plus 1/9 times the quantity x plus 5 cubed. Solving for x, let's first add 2 to both sides. So we have y plus 2 equals 1/9 times the quantity x plus 5 cubed. Now we'll multiply both sides by 9. So we'd have 9 times the quantity y plus 2 equals the quantity x plus 5 to the third. To undo the cube, we take the cube root of both sides. We could also raise both sides to the 1/3 power. So now we have the cube root of 9 times the quantity y plus 2 equals just x plus 5. When taking the cube root of both sides, remember we do not need a plus or minus on the left. So the last step, we subtract 5 on both sides. And again, x is equal to f of y. So f sub 2 of y over this interval is equal to the cube root of 9 times the quantity y plus 2 minus 5. And our last step is to define the left boundary on the closed interval from negative 2 to positive. And the last step is to define the left boundary when y is on the closed interval from negative 2 to 2. So notice how the left boundary is just along this one function here, which remember is the parabola, but now it's the left side of the parabola, which remember would be given by this equation here, x sub 2, because remember when y was 1, we determined that the x-coordinate would have to be negative 4 on the left side. So using this equation now, the left boundary is going to be f sub 1 of y equals negative square root of the quantity 2 minus y minus 3. So going back to our question, again, f sub 1 of y is equal to negative the square root of the quantity 2 minus y minus 3. So we can see in this question, defining the region using left and right boundaries is much more involved than using top and bottom boundaries. And this becomes important when we begin to set up double integrals to determine the limits of integration. I hope you found this helpful.